we have this question here. It says that P2 be the vector space of all polynomials of degree at most 2 over R. Okay, so P2 be a set of all polynomials of degree at most 2. Then we have a linear transformation T from which takes P2 to P2 be defined by T of A plus Bx plus Cx square is equals to A plus B plus B minus C into X plus A plus Cx square, right? So we have given some statements here. The first statement is that null space of T is alpha into minus 1 plus x square, such that alpha belongs to R. Range space is spanned by 1 plus x square and 1 plus x. Okay. And then we have T of 1 plus x is equals to 1 plus x square, and M is the metric representation of T with respect to the standard basis of P2. Then trace of matrix M is 3, right? So we have this statement. So let's see which of the statements are true, right? So for null space, what I'll have to do, I'll take all the elements which T takes to 0, right? For range space, I'll see that what kind of element T will map to, right? So let's see. Let's start with my first statement. It says that null space. So I can find out null space when I'll take Ta plus Bx plus Cx square is equals to 0, right? That means elements get mapped to, all the elements gets mapped to 0. So I'll have A plus B plus B minus C into X, and then we have A plus C x square is equals to 0. So from here I'll get A plus B is equals to 0, B minus C is equals to 0, and A is equals to minus C. So from here what would I get? That B is equals to C and A is equals to minus C and A is equals to minus B. So that means A is equals to minus B and equals to minus C. So if I'll take B is equals to 1, if I'll take B is equals to 1, I'll get null space of T is equals to null space of T. If I'll take B is equals to my alpha minus alpha, let's say null space, that would be alpha minus 1 plus x square, right? Where alpha belongs to real number. So this is my null space, because I'll get A is equals to minus B equals to minus C. So statement first is my true statement. Let's see my statement second, right? I am writing in the right here. Let's say statement second. So I have to find out range space. So how would I find out? I'll take the basis of P2x. What is the basis of P2x? 1x and x square. I'll see where I'll map these elements. So I'll find out T of 1. So T of 1 will be 1 plus x square, and T of x will be 1 plus x, and then T of x square will be minus x plus x square, right? So if I'll see these values, I can check that minus, I can write minus x plus x square as a linear combination of 1 plus x square minus 1 plus x. That means I can write T of x square is equals to T of x, T of 1 minus T of x, right? So that means, and range space has all the linearly independent elements. So in this case, range space will have these two elements, because the third one is dependent on the first two. So I'll get 1 plus x square comma 1 plus x. So that means statement 2 is also correct. Statement 2 is correct. Now let's see statement third. I have to find out T of 1 plus x. So let's first find out T of 1 plus x. T of 1 plus x, that would be A is equals to 1, B is equals to 1. That means 2 plus B, that means x, okay. And then we have A plus C, that means x square, right? Now T of 1 plus x means I have to apply T again over this polynomial, T of 2 plus x square, right? Yeah. Okay, now let's find out T of x plus 2 plus x square. So here 2 plus 1, I'll get 3, and B minus C. That means 1 minus 1, that would be 0, right? And then A plus C. Okay, so what would we get from here? 3 plus 3 x square, right? Let's check it again. If a is equals to 1, b is equals to 1, t of 1 plus x will be 1 plus 1 2, and then we have 1 minus, okay. Little bit error here, what we okay, let's do it again. Let's solve it again because I'm finding one error in solving, right? Okay, t of 1 plus x. Here a is equals to 1 and b is equals to 1, right? So a is equals to 1, b is equals to 1. What would we get? I'll get b minus c. That means 1 minus 0. That means x. And then a plus c. That means x square, right? Okay, so we have done the correct thing. T of 1 plus x. That would give me t of 2 plus x square, right? And a is equals to 2, b is equals to 1. That means 3 plus a is equals to 2, b is equals to 1, c is equals to 1. That means 0 into x plus a plus c. That means 2 plus 1. That means 3x square. So we get 3 into 1 plus x square. But they told me that it is 3. They said that it is t of 1 plus x is equals to 1 plus x square, which is not true. So third is incorrect. Now let's talk about option 4. M is a metric representation of 1x square with P2. Trace of matrix M is. So I have find out T of 1, T of x square here. So I can write down the matrix of M with respect to this basis B. Right? If I'll take this basis B, so I have find out the values at the elements of B of T. Right? So let's write down the matrix. It is 1 plus x square. That means 1, 0 and 1. Then we have 1 plus x, so that means 1 1 0, and then we have minus x plus x square, that means 0 minus 1 and 1. So I can see that that trace of M is equals to here 3. So that means fourth one is correct. So first correct, second correct, fourth correct, but third is incorrect. So which option matches? Option C matches to my answer. So here C is the correct answer. We have this question here. It says that T1 and T2 be the topologies be defined on natural number, where T1 is a topology generated by all the set which is 2n minus 1 comma 2n. So that means any open set in T1, that would be 2n minus 1 comma 2n. That means one odd number and one even number. And then we have T2, which is a discrete topology on n. So we have to find out which of the following statements are true. And the statements are: in n comma t1, every infinite subset as a limit point. And the second statement is, if I'll define function from t1 to t2, I'll get and the function is defined by this, that it is n by 2 if n is even, n plus 1 by 2 if n is odd. So I have to check that is it continuous function, and then I have to tell them which of the above statements are true, right? So let's start with the first statement. I have to prove that every infinite subset has a limit point. So let's take, I have to check, right? Let's take A be a subset of natural number, and A is an infinite subset of natural number, right? That is, it is infinite. And now, let's suppose if 2n belongs to A, if 2n belongs to A, then because 2n belongs to A, because we know that in the set B, in the set T, in the T1 topology, we have all the subsets which has a 2n minus 1 comma 2n. So if 2n belongs to A, then if I'll take every open set, then 2n minus 1 will be the limit point. Why? Then 2n minus 1 will be the limit point, will be the limit point. Why it is my limit point? Because if you will see, if you will take any open set, if I'm taking that 2n belongings to A, and if I'll take 2n minus 1 any open set containing 2n minus 1, then it has always some 2 into n belongings to it, right? Because if I take any open set, every open set containing 2n minus 1 always contains 2n, every open set S, right, containing 2n minus 1 always contain 2n, right? So that means this I can check that. Let's write it down as B, because I am taking here open set as B. So if I'll find out B intersection A is not equals to 5, so that means 2n minus 1 will be the limit point. So that means A has a limit point if 2n belongs to A. Now let's suppose if 2n minus 1 belongs to A, then 2n will be the limit point. Why? 2n will be the limit point because if I'll take will be the limit point, because if I'll take any 2n, if I'll take any open set containing 2n, then uh, it will always have 2n minus 1. So that means I'll get B intersection A is equal not equals to 5 in this case also. So that means A always has a limit point, either if it is has a kind of element 2n or it is has a kind of element 2n minus 1, then it will always has a limit point. So I can say that option first is my true statement, right? Now let's see option second, statement second. It says that f जो function defined किया है from t1 to t2, we have to check that it is a continuous function. So t2 is my discrete topology, right? T2 is discrete topology, so T2 has all the singleton sets open. So let's take this is my open set in T2, open in T2, right? So now to check continuity, I have to check that if f inverse n, this f inverse n is open, then I'll say that it is continuous. Other if it is not open, then I'll say it is discontinuous, right? So let's take this function fx is equals to uh, fx is equals to x, fx, let's define. Okay, what we can do here is that okay, so let's define fx is equals to n, right? How? When n is even, n is even, let's say x is even, because if I'll take, let's say, because if x is even, x is even, that I can take x is equals to 2 into n, that means I'll get fx is equals to x by 2, that is n, right? If x is odd, so x is of some type like x is equals to 2n minus 1 by 2. So when I'll solve fx, so what would I get? 2n minus 1 plus 1, right? 2n minus 1 plus 1 by 2. So what would we get? I'll get n, right? So I can define fx is equals to n for every x, either it is odd or even, right? This always be my always equals to n, right? Now what I can do here, I can find out f inverse of n. So let's find out f inverse of n. So it is all the elements of x, and what is this x are? X will always be 2n comma 2n minus 1, these type of element, because you can see that for particular n, if I have 2n, then I'll get n, for 2n minus 1, then I'll get n. So this is what, this is my open set, this is my open set, this is what B, and this is open set T1. So I'll say that f inverse n is open from here. F inverse n is open. If it is open, then that means f is continuous. So I get from here that f is continuous. So that means statement 2 is also correct. So which option is true here? Option A is correct answer. So we have given this question here. It says that P and Q lies between 1 and infinity, and we have some statements here that LP is a LP is a set of all elements where summation xi from 1 to infinity, xi to the power p over 1 to infinity is less than infinity, right? This sum is less than infinity, and for LP, capital LP, f is mu measurable, right? And this integral mod f to the power p integral over 0 to 1 d mu is less than infinity, right? So we have the statement that LP is contained in LQ, and it is capital LP over 0 closed interval 0 1 is contained in LQ over closed interval 0 1. So we have some results in functional analysis. This is a correct. This is completely based on our results, which we have results in functional analysis. These results can directly solve this problem, and if you have studied functional analysis, you will know this, that LP is contained in LQ. LP is contained in LQ if P is less than equal to Q, right? And LP's closed interval 0 1 is contained in LQ closed interval 0 comma 1 if Q is less than P. Q is less than equal to P, right? Q is less than equal to P. So here this is that P is strictly less than Q. So which one of the uh, statement, which one of the condition help? This will help, right? P is less than Q, so LP is contained in LQ, but this is not true, right? So first is true, second is not true. So option B is my correct answer here. So you have to remember this to solve this question. That small LP is contained in small LQ if P is less than Q, and capital LP is contained in capital LQ if Q is less than P.